2018.
Okay, all right.
Oh, okay. In fact, I haven't prepared for this. I just created the slides.
Don't worry.
So, okay, and anyway, so the paper is on variational bounds of mutual information. It's a joint work of Google Brain, Mila, and DeepMind, and it has been published in ICML2019. So here's the content of today's presentation. I will first give a very brief introduction of mutual information. That is, I will talk about its basics, and I will explain why this mutual information is really important in machine learning and also in the representation learning problem. And then I will talk about the bounds given in this paper, which is some lower bounds when a decoder is available, and also some bounds when a decoder is unavailable and we can only have a critic function, and also the upper bounds. And finally, I will lead us to discuss some issues in this paper. Okay, now first is the mutual information. The mutual information IXY is defined as the KL divergence between the joint distribution PXY and the multiplication of the marginals PX and PY. For the KL, it's defined as this. It's the expectation of the first term over the log of the first term divided by the second term. There are very nice properties of this mutual information. And if we search for the keyword mutual information in Wikipedia, we can find this Venn diagram. And in this diagram, the left side means the entropy of X, which is a random variable, and the right side is the circle which has the blue color is the the entropy of the random variable Y. And we can see that the mutual information IXY is the intersection of these two circles. So there are certain properties of this mutual information. We can have the IXY equals to HX minus HX condition on Y. This means, so for the first term HX, we can interpret it as the uncertainty of the random variable X, or the information it's our estimate of the uncertainty of the random variable X. And the X condition on Y is the uncertainty we have about X after we have know the Y random variable. So the mutual information actually told us how much uncertainties have been reduced after observing the Y variable. So how much uncertainties of the X have been reduced after observing the Y variable. And it's the same for the Y function. It's hy minus hy condition on X. So this is a very nice property of the mutual information. And we can find from this property, we can derive that the mutual information between X and Y is always larger or equal to 0. And the mutual information goes to 0 only if X and Y are independent. That means the mutual information is 0 because the Y tells nothing about X. So their mutual information is 0. And also, I like to introduce a very nice property of mutual information. So also, in fact, this one is related to the real world experience. So it states that the IXY is always larger or equal to IGX and FY. That means, so here we have the random variable X and the random variable Y. And we have some function to post-process X. the g function which gets gx, and the f function to post-process y which gets fy. And this inequality states that after this post-processing step, the mutual information will always be smaller. That's also called the data processing inequality, which means that post-processing can never increase information. And also, in fact, the inequality holds if and only if the G and F are invertible. And in fact, this property is also very interesting. That means if you are transforming X using some invertible function, it will never change the mutual information between X and Y. So it's like we can think of the mutual information as a way to measure the dependence between X and Y. Okay, so we can see that in fact, this property is very useful because if we use correlation to measure, like the Pearson's correlation to measure the dependence between two random variables, we are actually measuring the linear dependence. But for the mutual information, if we use it to measure the dependence between two random variables, we are measuring higher order the dependence of even the higher order moments. So that means the mutual information is the golden standard for test of independence and for measuring the dependence, and it's very useful for like in the independent component analysis, which we need to it's also called the cocktail party problem, where we observe the signal of multiple speakers, and we need to separate these speakers, and the only assumption that is that these speakers are independent. So we can use, like, we can minimize the mutual information between a pair of speakers. So that's how to use it to test for independence. But here for today, I like to emphasize its importance in representation learning. So now let's consider the very standard way to learn representation of an input X. And then we use an encoder which maps X to Y. And a natural way we like to optimize is, like, we like Y to capture as much information of X as possible, so we can maximize the mutual information between X and Y. Yeah, so if we so now here the mutual information so it plays some role in this representation problem. However, we can easily find that if we merely maximize the mutual information, it will not be very useful, because we can always like to copy the input and not learn the meaningful things. And in fact, for here we can try some other objective functions, like we add some noise to X, and which makes it X hat, and we use the encoder to encode X hat, and we measure the mutual information between X and F encoder X hat, and that is actually the way the objective function used in the stack denoising autoencoder.
So because since the mutual information is non-communicative for X and Y, right? So what is the intuition for?
It's communicative.
Communicative? Because the entropy is the entropy of X plus entropy of Y, then minus entropy of X, Y, right?
Yes.
Then yeah.
Yes.
This is communicative.
Yeah. So this one is communicative, and yeah.
Wait, what does communicative mean here?
So mean that you can swap
the order. It's like
Yeah.
Yes.
Okay. Commutative, yes.
Commutative, yes. IXY equals IYX.
Got it.
Okay. Okay, so here this is our objective function for learning some very useful encoder function FENC. The FENC here is the encoder. And the problem is how should we solve this optimization problem? And that comes to the problem to how to estimate the value of this neutral information. For the discrete case where the random variables are or discrete, it is simple because it's like we just keep a table of the joint xy of the joint distribution, and we can enumerate all the possibilities. And also if the distributions are continuous and they are Gaussian, we can get closed form result. And the difficult case is that the distributions are continuous and we have intractable the joint distribution, which is the focus of this paper. For this one, the traditional solution is based on we divide the x space and y space into multiple bins and to convert it to a discrete one and do the estimation. And also we can use some like k nearest neighborhood estimator, which also requires the binning step. And a very recent advancement in this area is like we can actually use variational method to estimate the mutual information. That is, we can think of to develop some upper bounds and lower bounds of the mutual information, which can sandwich the value. And then to estimate the mutual information, we can either to minimize the upper bound or maximize the lower bound. So to push it towards the value. And the final it's like in order to estimate the mutual information, we can like maximize the lower bound. So that's the focus of this paper. So that explains why bounds are very important for this mutual information. So now let's first consider the case of where we can have we can like use a decoder to approximate the posterior distribution Px given y. So here x is the input and y is the encoded states. So if we know x, the x may be the y may be encoded by x from some neural network. And then so we construct another decoder to map the state back to x, which is actually using the idea of autoencoder. And then so how could we divide a lower bound on this value? So now here our objective function is to, because it's a representation learning problem, our objective function is to maximize the mutual information between the input and the representation. And then how to use this proposal to do that. So here are some mathematics in how to derive this variational bound. So here the first line is just the definition of the mutual information, and then we multiply our variational distribution Qx conditional on y to both the numerator and the denominator. And then we find that the second term is some expectation of KL divergence. So for the KL divergence, it's always larger or equal to 0. So we can drop the second term and we can make the equality to inequality. So here we arrived at the first bound for mutual information, which is IXY is larger or equal to the expectation PXY log QX conditional on Y divide PX. And we can further simplify this to to like the first term and the entropy of X. So here we need to notice that the equality holds only if the proposal is equivalent to the exact posterior. So now if we like to maximize this mutual information and all the parameters are not related to X, so we can also drop the entropy term. And then we arrive at this objective function, which is actually saying that we first use an encoder to map the input to a state, and we try to use a decoder to reconstruct it back, which is exactly the objective in the autoencoder and also in the denoising autoencoder. So we can see that we can use neutral information to explain the objective of the autoencoder and the DAE. And so now it's the second part. So in some applications, it may be difficult to construct a decoder, and it's very common in some if the input X is high dimensional, it's very common. For example, if we consider Y is a vector and X is a video, so the Q function will be very complicated in order to map X to Y and to parameterize the probability. So that's the first problem of this encoder approach. And the second problem is that let's say that the previous bound has this entropy of X term. So this is still intractable because we do not know the entropy of the input. So the previous bound is only useful for maximizing the mutual information, but not for estimating it. So and the idea is here they also propose is that instead of using parameterizing the decoder explicitly, we use a critic function to parameterize it implicitly. It's similar as we can use an energy function to parameterize a distribution. And here they also choose to set Qx condition on Y to be this Px times the exponential of fxy. And here fxy, you can think of it as the score of the likelihood that x and y appears together if in this distribution. So it's like the energy function. If the score is high, the probability will also be high, and if it's a small score, and the probability will approach the 0. And zy here is to just a normalization term, and also called the partition function in machine learning. And we can also call it the partition function. And so zy is just the integral of the px efxy, which is then the expectation of px of e power fxy. And then we can put this qxy term into our previous bound, and we can find that it gives us this. So we just plug in this this critic form of this decoder function into our previous bound, and we can get this bound, which tells us it's the epxy fxy and also the epy log zy. So for here, since the zy function is still intractable, we need to further try some strategies to derive the lower bound. And the strategy used in this paper is based on this inequality, which is log x is less or equal to x over a plus log a minus 1 for any x and a which is larger than 0. And also the equality holds only if x is equal to A. And here, just to plug in this inequality into the log zy term. So it's like it will be zy divided by ay plus log zy minus 1. And then we can arrive at this term, and also we simplify it a little bit, we can get this term. It's the first item is 1 plus, so here it's the expectation which is calculated on the on the joint distribution of xy, and the energy function is log EFXY divided by AY. And also the second term, it's minus the multiplication of the marginals and EFXY AY. And in fact, we can think of it this way. So here, what we really want is like if x, y are if x and y are if x and y have a high dependency, and then we will encourage them to have a larger f function. So and then if they are independent, we will encourage them to have a smaller f function. So that's another like meaning of this term. So yes.
What is
AY? AY is a proposal. It's like it's called the variational distribution. So actually, so I will explain it in the next slide.
And also that's not equality. That's like the greater than.
Yes. So here it's the ITUBA. It's a lower bound of the mutual information, and it's called the TUBA lower bound. So here, and the problem and the way to do the things here is like we can use a neural network to parameterize the fxy and ay functions. So in fact, nowadays it's deep learning era, and we can use neural networks, and I think usually we can use some linear functions to parameterize the variational distribution. But here it's basically the same. So here we call the fxy as the score function and the ay as the baseline function. And for fxy, we can think of it as parameterized by some neural network. And we have some choices to formulate this score function. For example, we can choose it to be separable. So like we can first project the x and then project the y and compute the inner product to be the score of x and y. And also we can use joint modeling, like first concatenate x and y and feed it into a neural network. And for the baseline here, we can also use a neural network, and we can also fix the baseline to be 1. So if we fix the baseline to be 1, it will have the self-normalization effect, because we can see that for this term, actually we can put the denominator into the numerator, so it will not change the representational power of this term. And also for the AY, like we can use some exponential moving average of this EFXY term. Yes, and then we can get the algorithm for estimating the mutual information. So here we first initialize our variational distributions. It's f, theta, and a phi. And in each iteration, we first sample some mini-batch samples of XY pairs. And then we use the Monte Carlo estimation for these expectations to calculate the loss function. And then we compute the gradient with respect to theta and phi. and then finally we update CTM5 by gradient ascent, because we are maximizing the objective instead of minimizing it. So it's gradient ascent, not gradient descent. So, do you have any questions regarding this part? So that's a major algorithm for estimating the mutual information. So anyway, I will continue to introduce that. And so the previous bound has some problem in that it uses a single sample to estimate the critic, so estimate the F function. And what has been proposed in this paper is like we can use multiple samples to do the estimation, which is in fact to like draw another k-1 independent samples, and I will skip the math here. So finally we can get this INCE estimation of the mutual information. So we can see that so it's here it's similar to first we sample an X, and then we use encoder to get a Y related to this X, and also then we sample some X's that are independent of X, and then we can compare the score of these unrelated XY pairs and the score of this related XY pairs. So yes, so here that's the intuition of the INCE bound. And now they also conducted a very interesting experiment to justify or also to evaluate the effectiveness of different lower bound. So here the experiment is, so here we can see that if we like to train model to estimate the mutual information, we need to, like, for each iteration we draw some samples, but then we update the score function and also the baseline function. And then in the paper they also proposed to gradually increase the mutual information in this training phase. And so in order for some controlled experiment, they also choose a very simple X and Y combinations. That is, X is from a Gaussian and Y is a conditional Gaussian, is a Gaussian condition on X. And then because it's two Gaussian, we can get the exact closed form of the mutual information value. So in fact, the author chooses to gradually increase this rho value here. So here in the first stage, X and Y are not correlated, so rho is 0. X and Y are independent, and the covariance is like in the left side. So this is the covariance, and after some steps it increases the rho value. So you can see that X, Y becomes linearly more towards linear dependence. So the mutual information between X, Y also increases. And then later, at the third stage, it also further increases this rho value, which also increases the mutual information. And then what the author tells the network to do is to, for this type, to train the mutual information estimator using this data set. So it's like in the training phase, the value of the mutual information will increase, and they also asks the networks to follow different lower bounds to train to estimate this mutual information. And then the left side is the estimation of the single sample estimator, and the right side is the estimation of the multi-sample estimator. And so here we can see here for the left side the average. So the average is close to the ground truth, but it has a very high variance. So it's like if you check the loss function in your optimization, you can find it's shaking quite largely. So but for the right side, you can see that it's far from the ground truth, but it has smaller variance. And the author proposed we can actually balance the left side and right side, which arrives at a Newton. So what they are doing is to introduce an additional scalar alpha in the denominator to balance between the multi-sample lower bound and the unisample lower bound. So when the alpha is 0, it becomes the INCE lower bound, and when it's 0, it becomes the TUBA lower bound. So then we can tune the alpha to balance between the low bias, high variance estimator and the high bias, low variance estimator. So here the left side is the unisample estimator, and the rightmost side is the multi-sample estimator. And so in the middle, we change alpha to be different values. If the alpha is towards 0, it will be close to the NWJ, to the unisample lower bound. If it's towards 1, it will be close to the multi-sample lower bound. And we can see actually, so setting alpha, so it has the effect of like balancing this bias and variance.
Why are there 2 colors?
Yes. You mean the
blue and orange.
Yes. Okay. So here there are 2 colors. So it's so there's a blue line and the orange line. So they are using different ways to formulate the critic function. For the blue line, it formulates the critic as the concatenation of x and y and go through a neural network. For the orange line, it uses the separable form. It's like first map x and map y and compute the inner product. So we can see that jointly modeling the critic will arrive at a better performance. But also the complexity of modeling it jointly will be higher, because for every pair of x, y, we need to re-estimate the critic.
I don't understand the first row versus second row. So the second row is just multiplied by a constant in Q?
Yes. So
why?
Yeah. So I have said that so the mutual information between x and y is equal to mutual information between x and gy.
Yeah.
As long as g is invertible, and then it is conducting this experiment. So it's transforming the y to some log complicated transformations.
Is there a reason behind why they picked this particular function, or is it?
I think it's just random. So makes it look like yes, makes it invertible, but yes. So just pick any invertible function. But we can see that all these estimators do not perform very well if we transform the y here. So and that's so there are certainly problems in this in these estimators. Okay, so now so far I have only introduced the upper bounds. I introduced the lower bounds. So it's always mutual information larger or equal to something. And another thing is the upper bound. Sometimes we are also interested in minimizing the mutual information. So that means we want to ensure the x and y are independent. So when do we need to solve this problem? And in fact, this problem is it has some place in the independent component analysis, which I have previously briefly explained. So, and also it has also something to do with representation learning, which encourages the network to learn some disentangled representations. So here, so this is GIF taken from the D-sprites dataset, and for this dataset, it will generate the image based on 6 different factors, different independent factors: color, shape, scale, orientation, position of X, and position of Y. So these 6 factors are independent. And the problem is that is it possible to learn an encoder that can automatically discover these independent factors? And then what they are doing is that they are encouraging these factors, some certain elements in this representation to be as independent as possible. So they will need to use estimate the they will need to minimize the mutual information. And for so in order to minimize it, we need to derive an upper bound and minimize the upper bound. And in the paper, I will not go into the detail for this part. It introduces 2 upper bounds. One is a classical upper bound, and another is the so-called Lee-Wan upper bound. And then to learn disentangled representation, it tries to solve this objective function. So here we still would like the representation to have captured the meaningful information with respect to input. So we are still maximizing I, X, and Y. But now we would like the factors in this representational vector, for these elements in this representational vector to be as independent as possible. So and in the paper they use this form. It's like so this is called the total correlation in this paper. But actually, what it is doing is that it is saying that different elements in this vector capture different parts of the meaningful information. And also, it has added another term to encourage, like the encoded states will be stable with respect to a smaller noise. So and then the author conducted experiments using this objective function, and they find that the final learned representation is able to cover the X and the Y, the scale, but not the rotation in the D-sprite dataset. Okay, so in fact, so here it's what I need to talk about this paper, and then it's a discussion section. So how much time do we have? Oh yes, so we still have like 10 to 20 minutes to discuss about this paper. And here is what I have. Here are some potential ideas. So first, it's about BERT. So in fact, I have derived that actually the denoising autoencoder can be explained as by maximizing the mutual information. So in fact, the BERT objective is it's also a denoising autoencoder. So if we view it this way, it's possible to extend the objective function in BERT by using the bounds derived in this paper. So that's one potential direction. And also we can say that actually for this paper, it's deriving lower and upper bounds for the mutual information, which is the KL divergence between the joint and the product of the marginals. And we can like use not the KL but the Jensen-Shannon divergence. And maybe we can use similar techniques to derive bounds for this JST divergence, because sometimes the JSTs will be more stable than the KL, so maybe it will be more useful for representation learning. And then what I'm thinking is that we can further generalize these bounds to a more general form. So in fact, I have explained that. So for this type of bounds, it's actually encouraging the score function to score dependent samples to a larger value and independent samples to a smaller value. Then we can, similar to the GAN, so we can use two networks or two networks with some shared parameters, and then the first is V plus, and then it's V minus. And for the V plus, it's like we need to encourage these dependent. It's for the V plus, it will like give high score for dependent variables, and for the V minus, it will give low score for independent XYs. And yes, and this is also a direction to look into. And also we can think about like some better estimator of the partition function, because estimating the partition function is a well-studied part in machine learning. So here sometimes we can so here in the paper it tries to use some independent samples to estimate the Y, but we can also like draw some correlative samples using Markov chain Monte Carlo based methods, which sometimes will get a better sample efficiency. But for this part, I'm not very sure. And also there are some other ideas. And here I like to talk about two specific ideas. So the first one is about to change the objective function in the BERT or math, because BERT or math, they are basically the same. They are all denoising autoencoder, and then they are using the form like we here the M star function is some noisy so some function that put noise into X, and F theta is the encoder. And for BERT and math, we can all formulate it in this form. It's maximizing the mutual information between X and the encoded state of some noisy version of X. And then we can try to learn the masking strategy by solving this objective function. We use a network to mask the X, and then for this and then we use this minimax objective function for the masking strategy. It tries to minimize the mutual information between the encoded states and the original input. But for the encoder, it tries to maximize that. And the idea is that we are, for example, in BERT or math, we are actually like blanking out those very important entities in the sentence. So I think this objective will have this effect, and also it should be able to recover the whole word masking trick. And but we need to regularize the capacity of the masking strategy to avoid naive masking ways, which like we mask all the words. Okay, and another idea is to like we can use this kind of mutual information maximization to distill the knowledge of a large network to a smaller network. So it's like for BERT, we have many layers, like for example, 12 layers, and then we can shrink it to be 4 layers. And the problem is, how should we distill the knowledge? If we have this mutual information estimator, it will be simpler because we can maximize the mutual information between the states of the large BERT with the states of the small BERT. So then we can, then it's also an objective function to distill the knowledge. And so yes, so here then here is just 2 ideas of after I've read this paper, and this is a discussion part, so you may also like brainstorm about ideas and possible ways to use this mutual information. Also, maybe problems of this paper and anything. Yes.
Can you say a little bit more about the GSD divergence?
Yes, the GSD is
The metric version of KL.
yes, it's like there's the X and Y, so they are 2 random variables, and we construct another random variable which is equal to X plus Y divided by 2. It's the average of X and Y. So, and then it will be the KL between X and the average, and the KL between the average and Y. So, and then it's the average of these 2 terms. So we should still be able to use this trick in upper bounding the log function to derive a bound for the GSD. In fact, the GSD should be stabler than the KL.
It should be equivalent. It's just a metric version. There is still infinity you need to deal with.
Yes, but now in fact the mutual information is itself symmetric. So maybe there is no need to use the GSD. But yes.
So I have a question for the masking strategy for BERT. So as far as I understand, if we have a permutation-based autoregressive model like the XLNet, then they show that it can capture, or that there are certain dependencies that we cannot capture with the BERT style masking due to the independence of the masked tokens. Have you any thoughts on that? So in that sense, it seems like we should rather target this permutation-based autoregression objective in some sense, as it is more powerful, but then
Yes.
loses the connection here that you have with the autoencoding based.
Yes, in fact, for me, I prefer the autoencoding base because it can be faster. So, but yes, but we can also if we are able to solve this masking objective, then we can to learn some very powerful permutation which can fool the network. So and this strategy is also applicable to XLNet. But I think there are still some other problems of the XLNet paper, so I'm not sure which one would be better. In fact, in my opinion, maybe for representation learning, I'm not aware of the reason behind the autoregressive objective in XLNet, because languages are sequential in nature, and to permutate the language, I haven't found a very meaningful explanation. But for the BERT, I think it's looks more reasonable to me. Yes. I'm not sure. Maybe next time Faramas will introduce more about XLNet.
Okay, nice presentation. So for using mutual information to measure how the model is learning about representing the data. There's another usage that might be applicable. You can imagine using this maybe as a sampling strategy to design curriculum so that we speed up the sampling of important samples from a data set. That makes sense. So basically, a curriculum learning based on mutual information measure, you can decide that some sample already has very high mutual information between the representation and the data, and you don't need to run it again.
Yes, I think that's reasonable. So we can use this critic function to get a score. Anyway, I will use this. So we build a critic function, and then we choose the samples based on the score of the critic. Yes, and I think that will be useful. Yes.
That's why we might not need to run BERT on 50 gigabytes of data again.
Yes, I think that's a very nice idea. Yes. So in fact, if we consider it this way, yes. So in fact, the BERT here is using this encoder approach to derive the lower bound of mutual information. So maybe we can plug in another critic-based way to estimate the mutual information to decide the importance of the data, to decide whether the information of the data has been captured. I'm not sure.
Is mutual information used anywhere in the active learning community? Besides the importance of the sample?
I think it should have been applied in active learning. Maybe I may need to check the papers. But in fact, for this type of using variational bounds to estimate the mutual information, is some novel techniques. The first paper is published last year in ICML2018. So, and this is a very latest version. So it has derived lots of different lower and upper bounds. So maybe it has still not been applied to other areas.
Right? We're out of time.
Yeah, so thanks for everyone to join this meeting, and next time, I will send the invitation first, and Farmas will be presenting the XLNet after the KDD.
All right, looking forward to it. Okay, thank you.
Thanks for the presentation.